Welcome back. This video is brought to you by Forge College. In our previous lesson, we completed a survey of Solana development resources. Today, as you can read on our title card here, we are moving back to our module on understanding Ethereum's core infrastructure to unpack peer-to-peer networking and synchronization. If you picture thousands of independent computers scattered across the globe, all trying to agree on the exact same financial data at the exact same time, a practical question emerges. How do they pull this off without instantly crashing the internet? Imagine a giant metropolitan mailroom serving a massive city. If every single person in that city decided to mail a heavy encyclopedia to every other person at the exact same moment, the delivery trucks would jam the streets, and the entire logistical system would freeze up. Ethereum faces a similar challenge with its data. To avoid a digital traffic jam, the network operates like a highly organized and slightly gossipy postal service. It carefully sorts the light, quick notices from the heavy, bulky packages. The network survives its own massive scale by enforcing a strict operational separation. The process of knowing that new data exists is handled entirely differently than the process of actually downloading that data. Before any of that data can flow, a computer joining the network has to figure out who else is out there. This first step is a process called peer discovery. A new computer, which we call a node, sends out tiny digital pings to find candidates it can talk to. These candidates are identified by an Ethereum node record, or ENR. You can think of an ENR as a digital business card that holds a node's basic contact information. Once they find each other, they must make sure they can work together. Here is an animated diagram of this authentication. Two independent node entities exchange their ENR business cards, verify their protocol language, and establish a secure, locked connection link. Because computers are constantly turning on and off around the world, nodes must continuously curate and rotate their digital address books to ensure their connections remain active and healthy. Without this constant background cycle of discovering new peers and dropping unresponsive ones, a single node would end up completely isolated, unable to see the shared reality of the blockchain. Once a node has its active group of friends, it needs to talk to them. It does this using the gossip protocol, which is a rapid way to spread news to everyone nearby. This is headers first propagation. A central node broadcasts tiny announcement messages, like quick postcards, to multiple neighbors at the exact same time. A receiving node evaluates the postcard, identifies missing data, and requests the large shipping container payload containing the heavy data. If we skipped this step and forced nodes to blast those heavy shipping containers to every single peer by default, the network would instantly max out everyone's bandwidth and grind the validation process to a complete halt. This two-step cycle, announcing the postcard first, then selectively fetching the container, prevents duplicate data from clogging up the global digital highways. All of this explains how active nodes communicate. But what happens when a brand new node turns on, or an old one wakes up after a long vacation? It has to catch up to the current chain tip. One way to do this is called a full sync. In a full sync, the computer painstakingly downloads, unpacks, and independently double-checks every single piece of historical data since the network launched. This provides absolute trust because you are verifying the math yourself. However, processing years of history can easily take days or even weeks. For faster setup, there are alternatives. At the top of this timeline, you see the long sequential block-by-block progression of a full sync. Below, fast or snap sync make an abbreviated immediate jump to the current end by downloading a trusted state summary. Node operators make an active choice based on their immediate needs. They trade the absolute historical verification of a full sync for the immediate operational speed of a fast or snap sync. When we zoom out, we can see how peer discovery, gossip propagation, and synchronization all work together across the globe. It is a continuous rhythm. Thousands of nodes are constantly finding new peers, rapidly gossiping small postcards, selectively pulling down heavy containers, and quickly syncing up newcomers. The perfect alignment of thousands of computers is achieved through a carefully structured communication dance that balances the need for speed, trust, and bandwidth. In our next lesson, we will look at how real client configurations adjust these precise settings. Thank you for watching this video, created by Forge College. To dive deeper into this subject and explore our other Web3 educational materials, Simply follow the link on your screen and visit forge.college.